primer dependent. And finally, replication not only is primer dependent, but is discontinuous. So, as we look at a line force, what we see, the line force is moving in that direction on the discontinuous strand. It is primer dependent, 5' to 3', on a template that is anti-parallel, that is just the opposite. So what we're going to do next is see all of this together and see the steps that it takes to replicate the chromosome. Remember Cairns' observation, a Y fork there and a Y fork there. Yes. Yes. Anybody else before we start replicating a chromosome?
Is this primarily circular, or is this also
Well, so that's an interesting question. We are going to do replication in E. coli, which has a circular chromosome. But we're not going to see a circle except there. And so the actual mechanism applies to both bacteria and eukaryotes. The names of the enzymes and some minor details are a little bit different. And so we're just going to look at the big picture, the overall mechanism. But we are doing it in E. coli, and we are going to use E. coli terminology. But there's not that much that's specific for E. coli, just a few. The overall mechanism is a universal replication mechanism. Since those 5 things are universal in terms of living organisms, that is both bacteria and all eukaryotes. Only exceptions come in viruses, which have a variety of mechanisms, and mitochondria, which we talked about last week. Any last questions before we start replicating? All right. So first of all, we have a chromosome that looks like that, and we need to get the chromosome to look like that. So this form of the chromosome is very nice, easy to draw, easy to visualize. It's actually a variation called relax. Whereas this form of the chromosome is called supercoiling. You can think about supercoiling in the following way. If we nick, so these are the two double helices, double-stranded DNA. If we nick one strand, and so a nick is just breaking one ester bond in the phosphodiester bond, and then turn it around, twist the strand and reattach it, that DNA or rubber band is going to ride. So you've all taken rubber bands and seen how you can twist them and they rise up. It's not exactly the same because you're not cutting it, but it looks the same. And so inside of a cell, you never see the E. coli chromosome or any chromosome fully relaxed. What you see in a natural state in a living cell is a form that looks like that. Now, the only time you see the relaxed chromosome is in a dead cell. And so the cell puts energy into keeping its chromosome in the supercoiled form. And so before we can do anything for replication, we're going to have to relax the chromosome. And the enzyme that does that is called topoisomerase. And so this is step one. I'm going to list the steps here. So topoisomerase relaxes the chromosome. I'll list the enzyme and the function it does as we go through step by step how the bacteria replicates its chromosome. The reality is the bacteria doesn't relax the whole chromosome at once. You don't have to worry about that. It's going to do it section by section. But that's a minor point. Any questions on step one?
The circles that you have indicated in full animation, what are those centromeres? What are?
Bacteria doesn't have centromeres.
Okay, so what is that circle that you have? I guess it's called bottom. Yeah, that.
What circle?
Okay, and there was another one.
We go in.
Okay, because there was another one on the other animation on the top.
No.
Okay.
No. Anybody else? So remember, in this orientation, we have a unique site called ORI, O-R-I, which stands for the origin of replication. So this is a specific DNA sequence, and this is where the chromosome is going to be opened up. It's a specific DNA sequence, which means that it takes a specific protein. So proteins can read DNA, some proteins. And there's a specific protein that reads this sequence. So the next step, number 2, is open ORI, O-R-I. The protein is DNA A. And we're going to see a replication bubble just like that, only much smaller. So we have a little tiny bubble opened up by DNA A. Now what I'm going to do is convert from this so we're going to magnify that region. So we have a small little bubble. There's a problem. The whole chromosome is double-stranded. And that protects nucleic acids, both DNA and RNA. But now this bubble is open, it's single-stranded. There's no hydrogen bonds there. And so it's susceptible to breakage, but even more important, it's susceptible to enzymes which specifically cleave DNA and RNA. So we have to protect this bubble, and the way that we do that, so protect single-stranded DNA, the single-stranded binding protein. So we now have that. Single-stranded binding protein. So now we're ready to start assembling the enzymes at the replication fork, what we're going to do is just look at one fork. So we're going to go with a standard Y fork. Now, you have to understand that these single-stranded binding proteins are going to be with us for the whole trip. But they really mess up the picture, and so I'm not going to put them on again. You just have to keep in mind, as the Y fork moves and opens up, that whenever there's single-stranded DNA, that single-stranded DNA has to be protected with single-stranded binding proteins. Yes? So there's one protein that's actually called single-stranded binding protein. And that protein is the major one. There are other chromosomal proteins that function kind of like histones, but kind of not, no often. And so E. coli has a whole set of DNA binding proteins, most of which we're going to ignore.
As far as that step in the mechanism is concerned, there's only one type of protein.
Right, so right here, right now, that's the protein. There will be others, and I'm only going to give you the major proteins, not the minor proteins. Yes? Right, so it's exactly the ori itself and a little bit of DNA, a tiny bit of DNA around it. And so this is really a very, very small bubble. It's got single-stranded binding proteins, and it has DNA A. I should put that in also. The DNA A is here in green. So we have all of that there. And what you have to understand, just jumping ahead for a little bit, is that DNA polymerases are extremely limited in what they can do. All they can do is make a phosphodiester bond between two bases. They can't do anything else by themselves. We've already seen that, and that requires it. They can't even start replicating. It can only elongate a primer. And so this little bubble here, this Y fork that I've now greatly magnified, is a little tiny bubble. Actual machinery for replication is enormous. And so what we have to do now, once we open this up, is enlarge the bubble. The enzyme that does that is called helicase. So it enlarges the bubble and it moves the Y fork. That's just as important or more important. So the helicase is another enzyme like topoisomerase. It's an enzyme, but it's not doing any enzymatic action that you can see. It's not converting a substrate to a product like other enzymes. What helicase is doing is changing the DNA. And so in this case, what it's doing is greatly enlarging the bubble. And so that's a function of helicase, and helicase is going to stay on the Y fork because once it finishes enlarging the bubble, then its job is to move the Y fork around the chromosome. Remember, we're now only looking at the bottom of this bubble. The exact same thing, mirror image, is happening on the top half of the bubble. Just follow the 5', 3' around, and you see that it's going to be not identical, but mirror image. You got a question? Oh, I thought you were waving your hand. Okay. Anybody else?
So that single-stranded binding protein is like good in all these places where the
And so what's going to happen is we're going to coat it with single-stranded binding protein, and then all these things, starting with the helicase, is going to come in and displace single-stranded binding protein where it goes to work.
Is DNA A still there, or is that one not doing anything anymore?
So right now, DNA A is still there. We haven't gotten rid of it. I'm just not showing it. Anybody else? All right. So we're at step 4. We have the helicase there, and now with the helicase in place, we can bring in the primase, because we have to make an RNA primer. Did I say 5', 3'? Okay. 5', 3'. So now it becomes important that we have the labels on here. We're going to have to replicate both sides. So what we need a primer there, and a primer there. So that's the 5' end and the 3' end, and 5' end and the 3' end. Remember, you've got to keep your nucleic acids double-stranded, anti-parallel. Don't mess up anti-parallel. We have 5' here, opposite 3'. We have 3' there, opposite 5'. So the next step primase makes the primer. And remember, this is happening on both the bottom part of that bubble and mirror image on the top part. I'm not going to show that. Any questions? We're almost halfway through, 5 steps, and you don't even see DNA polymerase yet. So all of this stuff has to happen preliminary before we can even bring in the replication enzyme DNA pol 3. Because it can't do any of this stuff by itself. Yeah. Primers makes the primers on the template at the Y4. If there are 2 primers on the bottom half of the Y4 and 2 primers on the top half of the Y4.
Those primers are already coded on the screen itself.
It's an odd way of phrasing it. If the primers are just complementary wherever the RNA polymerase lands, and there does not seem to be any specific sequence, wherever you put the primase, it will make an RNA that's complementary to the template. That's the way it works. So not exactly the way you said it.
It's not particularly coded for on the strand.
It's not coded for like ORIG. ORIG is a defined sequence. It's found nowhere else. Primers are anything where it wants to start. And it's just location by geometry, not by sequence. Yeah. So 2 that I'm showing you here, and then 2 on the top Y4. primers get made, following standard rules, anti-parallel, 5' to 3'. All nucleic acids work 5' to 3' from the 3' to 5' template. Anybody else? And now, finally, you can bring in, what color do I want to use? You can bring in, that's a good color. DNA whole 3. Now you can consider steps 1 through 5 as initiation of replication. Now we're talking about elongation. So we have to go through all of these steps as the initiation process to start the process of replication. Once we're through that, and we have our 2 polymerases bound down here, 2 more bound on the Y fork above, now we're in the elongation phase. And so all of these processes, whether it's DNA synthesis, RNA synthesis, or protein synthesis, all have the same step. Initiation first, you have special requirements to start, then elongation, and then finally termination. Any questions? So we can now identify what's happening. This is the lagging strand. We are making Okazaki fragments on this strand. This is the forward strand. And so we're going to use blue for the helicase. The helicase and this Y fork, all it does is break hydrogen bonds. It's going to move the Y fork down, making that bubble that you see bigger and bigger. As one goes down, one Y fork goes down, the other Y fork goes up. Any questions on that? So we have DNA polymerase elongating the primer. Oh, the circle, the blue circle is helicase. The green circle is DNA pole 3. Red is the primer, black is the DNA. Any questions? Because now it's going to get complicated.
Can you spell Okazaki?
O-K-A-Z-A-K-I. Japanese name.
The DNA pole 3 always goes in the direction of 5' to 3'.
So all nucleic acid synthesizing enzymes only go 5' to 3' from a 3' to 5' template. Everything has to be anti-parallel. Anybody else? All right. So what's happening now? The helicase heliotrope on this Y fork is moving down, breaking all of these hydrogen bonds. And on the forward strand, it's just going to follow the heliotrope. Now we have a problem on the lagging strand. So the enzyme is moving up. The enzyme is now there. So we've got to replicate that segment. And so what's going to happen now, we're going to take the polymerase off. We're going to make a new primer there. We're going to put the enzyme there and make a second Okazaki fragment. And so this is now number 2 Okazaki fragment. Part of the elongation that elongate the primer. And so what we're going to do now is jump back up and start that step again. We don't have that problem on the forward strand. The forward strand just keeps following the heliotrope. But remember, a lagging strand is discontinuous, about 1,000 bases, about a kb. And so every 1,000 bases, we disconnect the polymerase, make a new primer, and elongate that primer. But now we have a problem here. First of all, we have RNA in the chromosome. Remember, we're doing this in E. coli, but yours works exactly the same way. You have RNA in the chromosome from the primers. And so what you have to do is remove the RNA. And we can use an enzyme called RNase H, or that enzyme that Kornberg discovered and got the Nobel Prize for, DNA Col1. It was shown not to be the replication enzyme, but it's still important and can and does function in replication. So the next step that we have to do is remove the primer. So we have a little bit of a problem here. DNA Col3, because it does nothing except make phosphodiester bonds, flies. It does 1,000 bases per second. It flies. Every second, we're going to make an Okazaki fragment. And so, depending on the timing here, if removing the primer is slow, we're going to have a gap. If removing the primer is fast, this will just go up and bump into the last Okazaki fragment. We're going to do it the easy way and assume that the primer was taken out. And so the Okazaki fragment has bumped into the last Okazaki fragment. And so it looks like this. And the key point is that we have a nick. A nick is one broken ester bond. And so the next step that we have to do connect Okazaki fragments. The enzyme is DNA ligase. The DNA ligase is a nick sealing enzyme. It cannot put a base in. The bases and the phosphate have to be there in the correct orientation. If the bases and a phosphate is there, you can make that ester bond to seal up the DNA. We don't have mixing of DNA. No organism can live like that because you can't supercut it. Seal it in. Connect the fragments. Or you're connecting two Okazaki fragments, two 1,000 base fragments. This is only happening on that lagging strand. The forward strand is just continuous all the way. Any questions on that? Like base. Yes. So DNA polymerase 1 can remove the primer and fill it in. So it does the same work. It's better than RNAs. RNAs can just remove the primer. DNA pol 1, because the DNA polymerase also, can remove the primer and fill in those 5 or 6 bases. So it's better to have that. No, it cannot see. These enzymes are extraordinarily specific. DNA pol 1 cannot seal the net. No matter what happens there, whether it's ribonuclease that takes it out or DNA pol 1, it cannot seal that net. DNA ligase has to come in at the end of every single Okazaki fragment and seal that fragment up.
Is it because there's no free phosphate?
No, there actually is. And so ligase can't put a phosphate in. There has to be a phosphate and an OH group there for it to seal it up. Just connects phosphate to OH. That's exactly right. Making an ester bond. Anybody else? So this goes on thousands of times. As that Y fork moves down, the other Y fork moves up, and eventually they meet. We are not going to talk about termination. It's kind of neat, but we're focusing on the synthesis part. Any questions on what we've done? 1,000 bases a second, an Okazaki fragment every second. That Y fork flies around the chromosome, but it's a big chromosome. Ever. Anybody else? Any questions on what we've done? And again, remember, on the other half, the top half of the Y fork, mirror image, the same thing is happening. Any questions on that? All right. So the same thing is happening when you look at your chromosome. Exact same mechanism. Only difference is that your chromosome Your chromosomes are linear. Bacteria does not have a problem because there's no telomere. So this is the end of your chromosome. On this strand here, synthesis just goes to the end. We erase the primer, fill it in, we seal it with ligase, this is E. coli. Now, we erase the primer. What do you think happens? Can you see any problem there?
It just stops.
There's a segment left over that's not copied.
What's that?
There's a segment left over that's not copied.
There's a segment left over, yeah. Based on what you know, and I'm telling you that it's correct, there is no way on earth, no enzyme on earth that can fill that in. It is absolutely impossible. That's the dilemma of a linear chromosome. Organisms with linear chromosomes have to come up with an alternative mechanism. What you basically do is ignore it. Your chromosomes are short, 5 or 6 bases, that's all they are. It's been known for decades, something called the Hayflick limit. It says that if you take one of your skin cells out and put it in cell culture, it'll only replicate for about 20 rounds, 20 divisions, and then stop. Because every division that it replicates just gets shorter and shorter and shorter. Same thing is happening here on the other side. Until it reaches a limit where the cell says it's getting too close to the good stuff. And the cell can no longer ever replicate again. And so this Hayflick limit, people determined years later, is because primers cannot be replaced. And so for the vast majority of your cells, that's life on a linear chromosome. But obviously, some cells have to replicate indefinitely. So if you want a really good cancer cell, cancer has to replicate indefinitely. You were a single cell fertilized egg. You have to replicate, I don't know, millions of times. And so there is a way around this. Actually, there are 2 ways around this. The first way is with an enzyme called telomerase. So this is just another replication enzyme, but it's specific for the telomere. It still can't replicate that. What telomerase does is extend that, because that's 5' to 3'. And so through a very complicated mechanism involving a combination, we're not going to get into it. Telomerase is the enzyme that you used when you were an embryo, a fertilized egg, to get around the problem at the telomere. Without that, you would only be about 1,000 cell embryo. Now, when this was discovered, I don't know, 10, 15 years ago, people thought, aha, we have the key to killing cancer. All we have to do is inhibit telomerase, and you can't have cancer, and you can't replicate indefinitely. But your cells are too smart for that. Every mechanism that you have that's essential for life, telomerase is a backup system. And so people thought they could just inhibit telomerase and cancer would stop. And it does. It slows down for a little bit, a day, a month, a week, and then it starts up again. You have a backup system involving recombination that doesn't need telomerase. Telomerase is better, but the backup crossing over system is just as good. You cannot stop cancer by killing telomerase. Good question.
Is that because if you stop telomerase, many of the surrounding cells, including globules, do die?
No, it's nothing to do with the surrounding cells, it's just the cell itself. If you stop telomerase, it'll stop the cell from
How are they part of the cancer cell? How are they part of the cancer cell?
Oh, well, so that's a different issue. Remember, the vast majority of your cells aren't replicating at all. It's just your stem cells replicating. And so there are targeting mechanisms to put drugs in specific cells. But that's a different issue. You cannot stop cell division by targeting telomerase. The cell has a backup system. It's pretty much foolproof. You can't get around the recombination system. So this is a mechanism that bacteria and circular chromosomes don't have to worry about. Any questions on that? Yeah.
So telomerase adds to the
Others.
other strand. How does it help us?
Because now when you start off here, you're starting off further out. on this, you're starting further out. But eventually, it's going to come to an end. Cell divisions. That you can go 20 cell divisions without telomerase before replication cell division stops. Anybody else? Okay. So this picture that I have here, this is a cartoon. This is not the real story of what the Y fork looks like. The real Y fork is a bit more complicated than that. So we have one enzyme there, one enzyme there. The reality is the replication enzyme is a dimer. And so these two enzymes, one on the lagging strand, one on the forward strand, the two replication enzymes tethered together. Otherwise, as you look at this, it's easy to imagine that the forward strand enzyme can run away because it's going much easier. It doesn't have to go on and off and on and off and make a new primer every second. And so to make sure that both strands replicate at the same rate, a pair of dimers, a pair of enzymes are connected together, and that forces the opposite strand into this loop. And so this is the reality. This is the real Y fork. And what we're going to do then is just start another primer there. And when the loop comes around, you just keep making Y forks, keep making oct172012 fragments by enlarging and shrinking that loop on the lagging side.
So now in your description you have on the left side, it's replicating, or the fork should it be replicating away from the fork? On the left side, your left strand?
On the left side, it's just going to follow. So the left side is the forward.
That's the fork, oh, okay, so.
So that's the forward side. That's the lagging, the oct172012 opposite fragment size is with the loop. And so because of that, it forces the DNA into this loop model. And again, this is all universal. Only thing that's not universal is this for a linear chromosome. But everything else, all of these steps that we talked about, that those are universal mechanisms, the specific names of some of the enzymes are a little bit different, but the process is exactly the same. Yes? Right. So, I mean, this works exactly the way I showed you, but the geometry is different. That's the only difference. Right, so there's a dimer here keeping the two strands. These two strands are going to run exactly together. So this one can't get ahead. Any last questions? Yeah, so the first one is the adherence, the second one is recombination. It's a complicated mechanism of recombination. Yes?
So the primer keeps forming inside the loop for the lagging strand?
Yes, that's right. Yep. Right, so the real replication enzyme is a dimer called 3.
I'm sorry, I missed that one, the C in the number.
There?
Above the four.
There? 1, 2.
Oh.
So this is not what the life form really looks like in the cell. That's a cartoon to make it easy to visualize. Just drawing all of that on that. Any last questions on how this works?
So, does nothing stand sort of get pulled through the,
That's exactly right. That's called the trombone model. That's the really,
and then it gets to like the, primer, it sort of pops off and starts to
that's exactly correct. You visualize it properly. Anybody else? Any last questions on replication? Yes. Right, so you gotta remove the primer. You've gotta remove the primer for the oct172012. If you don't have RNA, your chromosome is pure 100% DNA. Or DNA pole 1. Anybody else? You have that question?
is it the same thing that takes off the, primer of the four strands to the,
Yes, the enzymes, they're not exactly the same, but they're the same function. Different names that you carry. But the functions are absolutely the same. You've got to get rid of the primers. You do not have RNA in your DNA.
Primer is laying down primer on that lagging strand, and
That is way ahead, that's right. And so it's a complicated mechanism of measuring. By the way, your oct172012 fragments are short. Anybody else? Any last questions on replication? Okay, let's do an in-class cooperative learning exercise. It's a cooperative learning, so it is illegal to do it by yourself.
What's your name? Oh, thank you.
Oh, Megan up? I already have.
But free. Did you get this?
Extras? I don't have any more. Yep.
And that would be the lagging strand, that's the forward strand.
Said it's illegal to do it by us.
I know.
Do you put that on pause when you're doing this?
Nope. If I pause it, I'll have to do 2 videos.
Oh, because of
And until I get iMovie to work, it's just gonna have this sitting in there.
I'm just confused on
Which part? The box is up. Drug stuff.
Mommy.
Alright. I think it's a base pair. A and T.
Oh, I think they want
Oh,
structure.
Oh, that could be it.
dragons.
Oh, I don't want to draw that. It's gonna be so difficult. I forgot what A and T looked like. Wait. A is 2 parts, T is the hexagon thing. I'm gonna ask you guys first. I don't want to ask you.
Right here.
Do you want us to draw that for the part 3? Or is it saying something?
Yeah, no, draw this with the ribose chain connected to each other.
Okay. And then for this part it goes, is that 5, 3, 5, 3, 5.
Yeah, so the left side is the lagging. Yeah.
So this is just basically drawing like that backbone, and then
Kind of like how the homework was, but not both sides, just one side.
Alright. And then for this one you just want us to, just the A and the T, or do you want us to draw the...
The A and the T, yeah.
Okay.
And,
Do you know what they look like? Or
I know the
the
basic.
sugar's the house with a circle on top. And then on the right side
circle house.
there's a or T or C. It's a circle house. There's like a
Your oxygen. I think it goes C connected to the sugar, connected to O, connected to
what?
C,
No, I meant this way.
connected to another O. I'm a
Yeah, she wants us to draw that. Is that all she wants? Or does she
That's
want the
the-
compliment
the
too?
OH. Actually, that OH is
No?
that H isn't there anymore.
It's just OP.
It was condensated and goes into that one.
I wish I had some artistic talent. I want to ask her how we have to draw. Which is like, draw the other side, and bond.
I don't remember.
That seems like a lot of
A hydrogen bond
phosphates,
there,
so-
a hydrogen bond there, a hydrogen bond there to the other side. This one's a hydrogen bond there, and a hydrogen
That
bond
looks like too many phosphates.
It's supposed to be 3 phosphates. It's a triphosphate bond. And we never
Because I know
turn
in
these
the
things
book it
in.
goes O, P, then O, then it's connected to a C.
Can we turn
Because
these
then
things
there's
in?
two
'Cause I never-
oxygen bonds here. So I don't know. That seems wrong.
I know it's a triphosphate.
Otherwise, I fucked up on the homework.
I know
on
it's-
Wikipedia and that.
I'd look it up on my phone, but it's busy. It doesn't really matter. I just have to remember how many in there.
I know it's 3 phosphates.
3 phosphates next to 1 O, 1 P,
Or is it diphosphate?
It goes A to C, not P to TA.
So that's phosphodiester. It's 2 P.
I don't know how accurate he's going to want us to be.
On the one on
So
the-
I don't know if he's going to want us to, like, attach the 2 other oxygens to this P. Like, because there's 4 on phosphate.
Oh no, I'm just doing a basic.
Honestly, at this point, I
It
really
just says
just want it to
structure,
look somewhat right and not. Honestly, for me, on the test, it's going to look like this crap.
Because I don't know. Because I know it's not just carbons here, there's nitrogens and stuff like that. So this is actually kind of wrong. But if you look at it from a
Oh,
chemistry
that's
point
right.
of view.
Burkhead's been in the shop. I don't like it.
So they won't hear us talking on the video.
Oh, they're going to hear this.
Oh, so you're the one that posts the YouTube video.
What are you doing?
Say hi.
I'm going to have to delete this whole fucking thing.
And you don't.
Yeah, I do.
Why?
Because I just
He's gonna delete the sound.
it's not like he doesn't want it.
And they're on YouTube, so.
And he doesn't, he doesn't, no, they're not on YouTube, they're on unlisted.
Oh.
I could make him public if he's okay with it. Which just makes my life easier because I don't have to email anyone. It's just up to people to go to the page.
I like save all your emails.
Save all my emails. Thank you.
Because then I have the Connect.
I wonder if this would have been easier if I had been really good in kindergarten and drawn all my shapes. It's timing and it exactly, so.
Oh, it's on a phone time.
Huh?
That's on the phone time.
No, he started at exactly 12.
I'm not sure what color pen.
You don't have to draw all the hydrogen in here, the daily one. Because the difference between DNA and RNA is, in RNA, it's a hydroxyl.
This is just an oxygen, not a hydrogen.
The bottom one's an OH.
Yes.
Is this all you want, or do you want the...
Or no, it's a hydrogen.
No, that looks fine. You got the H on the 2' hydrogen,
The only reason
2'
why that H
carbon,
was
so that's good.
removed on this one is because it went through condensation.
So that was pretty fine, because I did T on top because I'm bad, but... That's okay, right? I mean, on the test, we have to switch them.
Yeah, you'd have to switch them around, but, you know.
That's just the basic structure, right?
Yeah, and keep in mind that you need phosphates coming off of this carbon and like a phosphate coming out of that one because it's all a part of the chain of nucleotides.
Do you want us to have, like, we should have this part going off of that part too?
Yeah.
Okay. I mean, as long as I know what to do, it's fine. This is what I'm going to study for the test. Just draw these over and over again, because I know we're going to have to draw one of these for the test.
See, what I want to know
He's going to
is
put C and G on it, and the book one is completely different from this one. So I'm going to be sitting there like...
see, what I want to know is just, on the test, does he want something basic like this? Or does he want the actual...
I think
considering the fact that his vocab has to be specifically to how he
I
would put
think-
it down, we want to memorize it as if you were...
I think for the picture, he wants you to make sure that you have all the things coming off, like what they were saying.
I
But your
have
general shape doesn't matter.
I have all 4 things in here, nucleotides, but it's just the basic.
No, we can ask him, like, what does he want us to draw? I wonder if I can bring an art student with me and just be like, just sit it down and be like, draw exactly what I thought you could draw. She wants everything coming
Because
off.
it's part of the actual chain.
I got a new folder, reminder, just for this class, because everyone filled up.
I do a notebook for each class, and then I just have like one of those big 3-inch binders that I stick all the notes in.
So just because you're more organized,
When I finish
doesn't
the
make you a
section.
better person.
Because like I no longer have everything from exam 1 in here. Only crap in here right now is stuff for exam 2. This is gonna be a fun exam.
My guess is it's on Halloween. Wait, no. Halloween is Wednesday, right?
Mm-hmm.
So November 2nd. First. Second? First. Second. Second.
I'm assuming it will be next week.
You would have said it by now.
No. Yes.
So next week, you'll probably see the
So,
test
yeah.
will be...
Unless he springs us on Friday. It'll be a week from Friday. Because I think I
hope.
asked him last week, and he said it was a week from Friday.
Well, that's disappointing. That means we have on next Friday.
No, it's the week after.
Okay, so it's
Not
November
next
2nd.
Friday, but the week after.
So that means we'll have one on we'll have one on November 2nd, one at the end of November, and then our final.
It won't be November 2nd. Yes, it will be November 2nd.
Are you gonna procrastinate like we're not supposed to and do it at 8:45? I tell myself I'm gonna do it at like night, and then it just doesn't happen until like I have to go to class.
I don't wake up like in time.
I wake up at 4 in the morning, so it's like
Why?
I should do it then, but I don't.
Why?
Once it like hits 4 o'clock, I just wake up and I'm like, can I go back to sleep? No.
I don't get out of bed until like half an hour before I have to leave.
I get stuff done in the morning. I mean, not really, like not important stuff. I sit around and play Minecraft because I don't have Legos anymore because I'm not like 10. I wish I had Legos still. What?
I like Legos. Legos are fun.
Minecraft. It's just it's
Make sure you don't like.
it's a no it's like a game where you're in a world made of blocks and you can just dig up the blocks and make whatever you want. It's really cool. It's like the best game ever made. It looks terrible too. It's just a Java thing, and it's like just little blocky things moving blocky stuff, and you just make these like huge towers, and then like pigs and cows and sheep will just randomly be there, but they're made of blocks too.
Sounds weird.
Yeah. I mean, it really is just like Legos, except...
I never play video games on my computer.
Why?
So I have a PS3.
It's on Xbox, too. But... We're going to talk about Dark Souls. Everyone who's listening in on this video now.
Dark Souls is a badass game.
Dark Souls is an awesome game. Watch your language, though.
That's when you just start cussing.
I did the Gravelord Covenant, so if you're ever playing Dark Souls and you're around like level 500, don't click on anything on the floor. If you're on the PS3. If you're on the Xbox 360, you're totally fine, because none of those people know how to play Dark Souls.
PS3 is so much better than Xbox.
No, it's not. I wish it was, but I don't have Dawnguard yet. And that's why I don't have Dishonored yet, because I'm boycotting Bethesda. Even though Bethesda just published it, and they have nothing to do with the game.
Oh, my game comes out at the end of the month.
It's
Assassin's Creed 3.
It's not at the end of the month. Remember, is it October 30th?
October 30th.
I know what I'm not studying for then.
Because I already have mine pre-ordered.
I do too. I have the collector's edition pre-ordered because I have nothing better to do.
I've had it pre-ordered since...
Assassin's Creed Revelations is out and they announced it. I had it pre-ordered back when I still worked at GameStop. Before they closed the store.
I gotta pre-order my next game, which comes out in March. God of War.
Really?
I love God of War. I own the entirety of it.
God of War 3 made me angry at the end of it, so I was like, I guess I'm not playing God of War again.
Well, God of War Ascension is a prequel.
I guess I'm not playing God of War again.
I actually liked God of War 3.
I liked God of War 3 until the very end, when it's like all this stuff about Pandora and having like some like retribution thing and thing for your family, and it's just like, you know what? God of War was not interesting because of this. It was interesting because you went around
Killing
just crazy. If I want to have like a nice like redemption, retribution story, I'll play Red Dead Redemption because it's really good, has a great story, and it's set up for that. God of War was not. God of War 3 starts off with you killing Poseidon, literally 12 minutes into the game. That is not a game that values anything, except for Pandora, who's like the representation of his family, who is also a box.
Well, God of War Ascension is before he even becomes...
So it's just him as random Spartan number 26? He doesn't have swords then. He doesn't have the Blades of Chaos or the Blades of Athena.
It's supposed to be before he makes his pact with...
So it's going to be him with a spear, because if they're being historically accurate, he had a spear and a shield, and swords were for bad people.
I don't know. I know that's going to have some really cool characters. I have it on my Facebook, so they post pictures of it all the time.
So,
they've got Achilles, they've got...
Why would Achilles be in there?
I don't know, they've got all the different war heroes. Oh god, what was the other one? They
That's
had Achilles.
terrible. Now you're gonna have to be like, well, I guess Achilles was pretty cool. So Kratos came along, and I guess he was the one who probably shot him with a poison arrow too in his ankle. That must have been like a
Well,
really good
you
shot.
kill a whole bunch of heroes in
If you
God
think
of
about
War.
that was like whoever did that was like really lucky. Unless they were just firing arrows like crazy, and then one guy just hit because there was like arrows all over his body.
Well, if you
Looked
go
like
by
a
the
hedgehog.
movie,
Yeah, if you go by the movie, he just got shot once by like random.
well, that was his Achilles heel.
I know. That's like a difficult shot. Most people like to wear shoes.
Couple of things to comment on.
Well, in Greek they wore sandals.
As exam is coming up, you've got to learn the basics. I will not give you anything like this on the exam. This is open book. The exam is not. We will have a nucleotide on the exam. You've got to learn the structure of the bases. Most everybody knows the sugar. Just be careful to show all the details. You've got to show the hydrogen on the 2' carbon. You can't just use a line to represent it. This is not biochemistry. You have to show me the elements. And so you will not get a nucleotide. You will not get a base pair like you had on the homework. I will just pick one nucleotide. There are 12 of them. I will just pick one out of the hat and have you do that for the exam. So make sure you get those bases down. So the last part of this chapter is recombination. We talked a lot about recombination. We saw recombination of crossing over first when we did meiosis, with prophase 1, and then we saw recombination again in bacterial genetics, that bacteria have one single recombination mechanism, but multiple transfer mechanisms. In general, we can divide recombination into two different types of recombination. Legitimate recombination requires homology. So legitimate recombination requires that the two strands of DNA doesn't have to be exactly the same, or you don't have any advantage of making new combinations of alleles, but the two strands have to be similar. And then there's illegitimate. So illegitimate means no homology. You can divide legitimate into two different flavors, and that is general recombination, large regions of homology, versus what's called site-specific, small regions of homology. Can anybody think of an example of general recombination?
Introns? Introns?
Introns? No, not at all. Where are we talking about large recombination?
For some types of gene causes testicles to form on the Y chromosome, sometimes there's like a mixture.
No, you're going way too complicated. What have we done in class? What's that? I can't hear you. So lytic cycle. Well, tell me exactly what you mean. What part of the lytic cycle? Fragmenting the whole DNA is not recombination. That's the destruction of a chromosome. Where are we seeing recombination involving large regions of DNA? Crossing over. What kind of crossing over? Where? When? You mean like meiosis? Meiotic recombination. Also, all the bacterial recombination. Chromosome size species. Site-specific is kind of tricky. Where have we seen site-specific? We actually done it in class. Where do we see little tiny regions of homology leading to crossing over?
Viral.
No, if by viral you mean two virus chromosomes recombining, that's general. That's the same as meiosis. What do you mean by excision? Okay, how about doing it in reverse? How do we get in? How about integration? Phage integration. A little tiny part of phage lambda is homologous to a little tiny part of E. coli. One last thing, where do we see illegitimate? Where do we see illegitimate recombination? Going on as we talk right now in your body. Jumping genes, yeah. For transposable elements. Jumping genes excise and integrate without any specificity. When we come back on Friday, what we are going to look at is the mechanism